All right, so let me talk some about this. So catalysts could make this thing go faster. A catalyst could make this go faster. And catalysts made of protein are called enzymes. Okay. And they're named usually X-ACE. They always have this ASE ending, usually. And these are better than heat because they speed up specific reactions, which gives you control. That is, if you remember, there's two ways to speed up a chemical reaction. You can heat it, or you can add a catalyst. Problem is, again, another reason, so one of the reasons the living things can't use heat is because you can't get hotter than a certain amount or you're in trouble. But also, heating speeds up every reaction. I don't want every reaction to happen. I only want certain ones. So by adding a catalyst gives you control over what happens. And there are probably millions of different ones, different enzymes, each for a different reaction. So make specific catalysts for each one. They are an essential part of all cells. You could not live without thousands of different enzymes doing their job all the time. So let me give you an example. Catalase, it's not a great name, but it has that ace at the ending, catalyzes the breakdown of hydrogen peroxide. Okay? That is, and we would write the reaction this way: 2 hydrogen peroxide, and you'd say catalase catalyzes the reaction, turning into oxygen plus 2 molecules of water. And the delta G is negative. And in enzymatic reactions, we call the starting thing, the reactant, is called a substrate. I don't really know why they don't call it a reactant, but they don't. And this is called the products. Okay. And why do you have this? Turns out that hydrogen peroxide is toxic, therefore you need to detoxify. That is, it turns out, I showed you that reaction was reversible. In the presence of oxygen and water and a certain amount of energy, you can get some hydrogen peroxide formed. So any glass of water in it will have a little bit of hydrogen peroxide just sitting there, right? And that's toxic, it's nasty. So cells have developed a way to break that down, to try to keep the concentration as low as they can, because hydrogen peroxide is toxic in a variety of different ways having to do with that peroxide bond, all right? So all living things, every living thing that lives in an oxygen atmosphere, which most living things on Earth, have catalase because they want to get rid of the hydrogen peroxide that forms accidentally to keep themselves protected from it. So how does an enzyme speed a reaction? The answer is they bond to the transition state. There's several ways to think about it. This is the most precise way, via H bonds, etc., depending on the substrate. And this works because since making bonds is delta G negative, it makes the energy of the transition state lower, because you're making bonds there, which means a lower activation energy means a faster reaction. So there's a couple ways to look at it. When I first learned about these, I thought about it as a little machine. You know, grabs its substrate, gives it a twist, and it comes out as product. It's not a bad way to think about it. Right? Another way to think about it is that grabs onto the substrate and sort of bends it into the product. It turns out it's actually simpler than that. All you have to do is bind to the transition state, not the reactant, not the product, but the thing in the middle. That's all you have to do is has bonds to the transition state. Because bonds are delta G negative, so that transition state now is going to have a lower energy because now it's the bonded to the enzyme transition state. Not covalent bonds, but ionic, hydrogen, hydrophobic, all that stuff. You've lowered the hill that molecules have to get over, so more of them can get over it. So it's just as simple as binding the transition state, it turns out, is all there is to it. I want to show you some about what I mean by that in a second. There's a note here that the enzyme is not changed by the reaction, therefore can be reused, therefore it's very fast. So an enzyme does its thing. Try that one last time, very fast. The idea is it doesn't just do a reaction once, it does it over and over and over and over and over, so it makes a big difference in how fast things can go. So let me show you what I mean by that, and I want to show you an animation. So you can do a cartoon if you have, and it's classic to use a sort of Pac-Man looking thing, catalase, and then hydrogen peroxide comes in and binds to what's called the active site, which is where the action happens. H2O2 binds, and now you've got H2O2 at the active site, then you have the reaction, and then O2 and water are released. And then this thing gets recycled. So you can do it over and 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 over. So, for example, if you had a sample of catalase and you added it to a bottle of hydrogen peroxide, the fizz would go out of it in a hurry. So, for example, actually, if you take it's the catalase in your tissues, actually. When you put hydrogen peroxide on a cut, it fizzes like crazy. And the reason for that is that your blood has a lot of catalase in it. It's catalyzing the breakdown of hydrogen peroxide to oxygen, making bubbles. So a drop of blood, if you put it in there, would make it fizz in a big way. Or even any piece of any living thing. So like a piece of meat, or even, you can try this at home, you can put little bits of potato or carrot in a little glass of hydrogen peroxide, and you'll see bubbles coming off of it because the catalase is breaking down the hydrogen peroxide. And that will keep going until all the hydrogen peroxide is gone, because the catalase does it again and again and again. It doesn't get used up. It keeps going and going and going and going, doing its job until there's no more hydrogen peroxide left. Questions about that before I show you a little bit about how the enzyme can do it? Okay. So for this there are no figures, but it's very similar to the first one, so I want to give you a sense of what's going on. So here, same old energy diagram. This big blob goober up here is the enzyme, and here's our two hydrogen peroxides. And if you remember what I said about what a catalyst does, is it changes the pathway to make it easier. So instead of having to wait for one of these bonds to break, it's going to find a new way to do it. And so if you watch the mechanism of this, the start and the end are the same, but the getting there is different. So what happens is, the first thing is the first hydrogen peroxide comes in and binds to the active site. And how does it bind? Hydrogen bonds, ionic bonds, et cetera, et cetera. And the first thing it does is the active site swipes a hydrogen. You see that going on up there. Swipes a hydrogen, and then actually goes and sticks that hydrogen, or it actually saves that hydrogen for later. And then one of the bonds, now here's the trick. If I was sure, this is like the secret to how this whole thing works. This is the bond between those two oxygens. That's the hard one to break. And if you remember in the uncatalyzed version, you got to just bust this and hope that you get future gain down the line. What the enzyme does is it makes a swap. So first it's bound here, and then it swaps to bound someplace else. So you're trading a bond for another. So the net is close to free energy zero because you're just trading one bond for another. So it makes the process easier because okay, I'm going to break a bond that's going to take some energy input, but I'm making one immediately. That is right over here to the enzyme. And then there's sort of more song and dance. The other one comes in, some more swaparoo, blah, 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 et cetera, and you end up giving off oxygen and water. And the enzyme is back to the way it started. So again, the secret of this is it makes that bond breaking a trade. Instead of just giving up a bond, you're getting a new one. So you break a bond, you break a bond, but you also make a new one. And so the result is our following the bouncing ball has a cheat. It doesn't have to go over the high hill. It goes over a much lower hill. And what that means is more molecules at room temperature have enough energy to make it over the hill. So when you drop a piece of a liver or drop of blood or you put it on your skin, whatever, the reaction can happen much, much faster because more molecules have enough energy. And again, then the enzyme gets used again and again and again. Questions about that before we talk more stuff? All right. Let me show you one thing. If you look at the next page of today's information-packed handout, there are some pictures. I just want to show you a little bit about what catalase looks like. So, and these are still pictures from this, so you don't have to draw it. Catalase is, as you would expect, a big blob of atoms. It's actually made of 4 chains, it turns out, although not 2 alphas and 2 betas, but 4 identical chains stuck together. And if you look at them, they're color-coded. It's actually different than hemoglobin. Hemoglobin was like 2 apples and 2 oranges kind of stuck together. These, you see the light blue, they're really intertwined in each other. They sort of plug in one to the other, and they're really sort of more tightly held together, the 4 chains. The other thing is, each chain, has a little tunnel. That green part, or if you see a little bit, is the active site. Right at the very, let me turn that around so you can see it better. The active sites are in purple, and so you have to line it up just right. But there's a guide. The yellow and the green is a guide, and then deep in the center there's a red, and sometimes if you line it up just right, you can see the purple. But basically, the hydrogen peroxide shoots in those holes and reacts, and oxygen comes out. So if you think about it, oxygen is about the size of 2 of those balls. So it's much, 2 atoms, H2O2, a little bit of hydrogen stuck on. So it's much, much smaller than the enzyme. And the enzyme has actually each molecule of the enzyme has 4 different places that can react. And then there's actually, if you zoom in on the enzyme, it's a little hard to say, on the inside, there are a bunch of amino acid side chains, these ones here and here, that actually, you can't really see it. So, but it's basically the main point is deep in the active site, there are a bunch of side chains that hold everything right in place. All right. Last questions on this before we take it one further step.